In a remarkable breakthrough, astronomers have pinpointed the very moment when planets begin to form around a distant star, something never achieved before. By combining observations from the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, scientists captured the earliest seeds of planet formation condensing out of hot gas around a newborn star. The discovery offers an unprecedented window into the birth of a solar system, allowing us to witness a process analogous to how our own solar system formed 4.6 billion years ago. Published in Nature on July 16, 2025, this finding represents a leap forward in understanding how worlds like Earth come to be. Astronomers have long studied protoplanetary disks around young stars, but until now they either found fully formed newborn planets or only the raw gas and dust disks before solid particles appear. This new observation is fundamentally different. It catches the birth of planets at the very start, when the first tiny solid grains coalesce. Melissa McClure of Leiden University, lead author of the study, said, "For the first time, we have identified the earliest moment when planet formation is initiated around a star other than our Sun." Co-author Merrill Van't Hoff, Purdue University, likened the discovery to getting a picture of the baby solar system, noting that HOPS 315 looks like our Sun and planets did when they were just beginning to form. What exactly did the scientists see? Hot mineral dust, the first solid matter in the planet-making process, condensing out of the gas within the star's disk. In our own solar system's history, such high-temperature minerals, rich in silicon monoxide, for example, were the first solids to appear as the Sun's protoplanetary disk cooled. Over time, these grains stuck together to form larger pebbles, then boulders, eventually growing into kilometer-sized planetesimals, the seeds of planets like Earth, or the cores of gas giants. Until now, astronomers had never witnessed this initial condensing of dust in real time around another star. It was purely theorized based on meteorite evidence. This process has never been seen before in a protoplanetary disk, or anywhere outside our solar system, said co-author Edwin Bergen, University of Michigan. The new observations of HOPS 315 prove that this critical first step of planet formation is indeed happening in the cosmos, just as it once did here. Importantly, the team observed that the silicon monoxide, SiO, around HOPS 315 exists in two states, as gas and as part of newly forming crystalline solids. This indicates the minerals are only just beginning to solidify out of the hot gas, essentially capturing the flashpoint when a planet-forming disk starts turning from gas to rock. We're seeing a system that looks like what our solar system looked like when it was just beginning to form, Van't Hoff explained, emphasizing how exceptional it is to catch a star at this early evolutionary stage. The finding truly marks the dawn of a new planetary system, as the ESO European Southern Observatory press release described it. The star at the center of this discovery, HOPS 315, is a relatively small protostar, about 0.6 times the mass of the Sun, located roughly 1,300 to 1,400 light years away in the constellation Orion. It lies within the Orion B molecular cloud, a stellar nursery teeming with newborn stars. HOPS 315 is a Class 0 protostar, essentially a star in its infancy that has only recently begun fusing hydrogen or is on the verge of ignition. At this tender age, likely only tens of thousands of years old, it is still cocooned inside the dense cloud of gas and dust from which it formed. Think of this cloud as a womb or feeding envelope. Material is actively accreting onto the young star, and some is flattening into a rotating disk around it. What makes HOPS 315 special is how fortuitously we can observe it. Typically, these infant stars are enshrouded by thick cosmic clouds that hide their inner workings. However, HOPS 315 is oriented at just a right angle relative to Earth, with a cavity in its surrounding envelope that lets us peek directly at the inner disk. This system is a unicorn, said Fred Ciesla, a University of Chicago scientist who reviewed the research. It has a hot inner disk that's still going through this early phase, and it's oriented so we can actually see it. That makes it very special. In other words, by lucky geometry, we have a clear line of sight to the crucial region around HOPS 315, where planets are starting to brew, whereas most such protostars keep their secrets hidden behind opaque dust clouds. HOPS 315 thus serves as an analog of the nascent sun. It's expected to eventually grow into a sun-like star, and right now it's showcasing what our solar system might have looked like at time zero. All the ingredients are familiar: a young sun-like star, a spinning protoplanetary disk of gas and dust around it, and within that disk, the first sparks of planet formation. The system even resides in Orion, ironically, the same constellation that contains the Orion Nebula, often studied as an analogy for our sun's birthplace. By studying HOPS 315, scientists effectively travel back 4.6 billion years to witness scenes from our own origin story. JWST's infrared spectra told them what ingredients were present, SiO gas and silicate dust, and in what state, while ALMA's imaging showed where those ingredients reside, a tight inner disk region. The combination was crucial. JWST alone might have detected the signature but left ambiguity about whether it came from the disk or perhaps a protostar's jets, while ALMA alone could map dust and gas but not identify their composition with such specificity. Together, James Webb Space Telescope and Atacama Large Millimeter Array provided a complete picture of an embryonic planetary system. As ESO astronomer Elizabeth Humphreys, not involved in the study, highlighted, this result shows a very early stage of planet formation and highlights the combined strength of JWST and ALMA for exploring protoplanetary disks. How do these observations connect to our understanding of planet formation? They essentially confirm a long-suspected sequence: hot primordial gas cooling into dust, dust clumping into rocks, and rocks building planets. In the case of HOPS 315, we are witnessing the moment of dust creation, when the temperature in the inner disk fell enough for certain high-temperature minerals to crystallize out of the vapor. In astronomy, these first condensed solids often take the form of refractory minerals, those that solidify at very high temperatures. A prime example from our solar system are the so-called CAIs, calcium aluminum rich inclusions found in ancient meteorites. CAIs are white, millimeter-sized nuggets embedded in some meteorites, and laboratory dating shows they are the oldest solid materials formed in our solar system, effectively marking time zero for planet formation. They likely formed close to the young sun in a hot disk environment, then later got incorporated into asteroids which fell to Earth as meteorites. The HOPS 315 observations provide direct evidence of this gas-to-solid transition. The data show silicon monoxide gas is present in the inner disk and that solid silicate particles are forming there simultaneously. In practical terms, we are seeing the creation of the very first rocks that will eventually build planets. Those solidifying minerals are analogous to the CAIs and other refractory inclusions that kick-started the planet-making process in our solar system. Once formed, they can begin glomming together under their mutual gravity. Indeed, one of the intriguing clues from HOPS 315 is that a large fraction of the silicon has vanished from the gas phase. JWST detected that the outflow jet from the protostar is missing about 98% of the silicon one would expect to see, relative to other elements like carbon. That may be a hint that planetesimals are already forming there in a similar way that they must have in our solar system, McClure speculated. In other words, the silicon isn't in the gas or jet because it's been locked up in solid dust grains or larger rocks in the disk. This is a tantalizing sign that the process has advanced from mere dust grains, perhaps, to actual pebble-sized or larger bodies hidden in the disk, essentially early planetesimals. Being able to witness the birth of a new solar system carries profound implications. For one, HOPS 315 now serves as a time machine for understanding our own cosmic origins. AOPS 315 can be used to understand how our own solar system formed, said ESO's Elizabeth Humphreys, emphasizing how closely this system resembles the early sun. By studying it, we can test theories of planet formation directly. For example, models predict that CAI light grains should appear in the innermost disk within the first approximately 100,000 years of a protostar's life. The new observations indeed show such grains forming at around 1 to 2 astronomical units from an approximately 0.1 million year old protostar, aligning with those models. This new work strongly suggests that, for HOPS 315, conditions suitable for CAI formation occur within about 1 Earth-Sun distance at an early time, a fraction of a million years after a protostar's formation, noted Phil Armitage, a theorist at Stony Brook University, commenting on the study. That consistency with theory isn't necessarily surprising, he added, but actually seeing it gives astronomers confidence that their timelines and chemistry for planet birth are on the right track. The observation of HOPS 315's infant disk has given astronomers an unprecedented front row seat to the birth of a new solar system. It confirms decades of theory by directly capturing the transition from hot gas to solid planet-making material, at the same location and stage that our own planetary system likely passed through. This breakthrough not only illuminates our solar system's murky past, but also marks a milestone in our quest to understand how common, or rare, the formation of Earth-like worlds may be in the universe. The cosmos has allowed us a precious peek at its creative process, and with tools like JWST and ALMA, we stand better equipped than ever to witness the genesis of worlds.